You have been introduced to the idea of work and energy in your class and your textbook and Mr. Swain's videos. So I'll just sort of give you a little overview from my point of view. The way all textbooks always start off talking about energy is by defining something called work, where work is defined to be the component of some force along a distance s times s. So if you have an object of mass m on which you are exerting a force F, and that object moves while you're pulling with that force F through some displacement S, then this magnitude of this vector is S, and the component of this vector along S is F sub S, and we then have the definition of work. This seems sort of ad hoc, and it sort of seems also, it's tempting to think that this is some new fundamental thing. In other words, where did this thing called work come from? Well, just between you and me, work is introduced first because someone already knows the answer. Someone has worked backwards and found that this quantity is important. Very important things to notice about work is that perhaps the most important thing is that it's a scalar. It's not a vector. However, it can be either positive or negative, because if S is this way and F sub S is this way, okay, then the component of F along S is negative F sub S. So think of S, if you like, as being X, the positive X direction. The direction in which the particle actually moves is called the positive coordinate direction. So in this case, up here, the work is positive. In this case down here, the work is negative. Now, let's just simply ask ourselves what this means in terms of what we've already learned about Newton's second law. In this case, where the work is positive, if the object is originally going with some speed, some velocity v1, then later it will be going with some larger velocity v2. Whereas down here, if it moves a distance s, when it's here, it'll have some velocity v1. When it's here, it'll have some smaller velocity v2. Okay? So, before I actually ask what is it that work does to something, I want to emphasize something. There is really nothing new in this whole work and energy unit. Textbooks always make it look like this is some new fundamental kind of physics. But all it is Newton's laws looked at from a different angle. Now, why would you want to look at it from a different angle? It seemed like what we had already worked just fine. Well, it does work just fine, but problem solving can be very difficult. Let's take a simple example. Okay, suppose that we have you've all seen this. We have a simple pendulum of mass m, and we pull it back at some angle theta, and we let go of it. Okay, we let go of it, and it starts swinging down until it gets down here, and when it gets down here, it has some speed v. How fast is it going? Well, you say, well, that should be easy enough. Okay, all I have to do is do Newton's second law, find out what the acceleration is. So let's look at this mass at some particular time and say, what are all the forces on it? So choose a body, I choose the mass. There is its own weight, mg, down like this. Okay. There is some tension in the string, T, like this. And those are all the forces. And so now what we could do is we could choose a coordinate system like this. And we could call this the plus x-axis. And we could say that we resolve our forces like this. And here is the angle theta. So at this particular time, the acceleration, so the sum of the forces in my x direction is equal to the mass of this thing times the acceleration in the x direction. And that's equal to what? mg times the sine of theta. Well, here's the problem. The acceleration is always changing, okay? Because theta is always changing. And so it's not a simple case now where we can say, okay, well, the acceleration is, this is only the acceleration a sub x as a function of theta. Okay? And this is going to be some function of theta. In fact, this problem can't actually be solved in closed form on a piece of paper, okay? That is to say, trying to find out what a sub x of theta is, let's just simply say it's enormously hard. On the other hand, as we will see, it'll turn out to be enormously simple to find out how fast this guy is going when he gets to the bottom, or anywhere along its path. We could find the velocity as a function of position. What we can't find is the velocity as a function of time. Okay, so that's basically what we're doing here. Is what energy really is finding a clever new way to apply Newton's laws to make problem solving easier. Okay, so let's go back now and talk about work. Okay, so I'm going to assume that the force is constant, and just for simplicity of notation, let's say that x is the distance that the thing moves, okay? Or I should maybe, well, let's just say x, let's say that the object starts off at x equals 0, and it ends up at some position x, and I'm assuming that, so here's my mass, here's the vector x, if you like, and I'm going to assume that, just to keep things simple, that f sub x is like this, okay? So f sub x is just, I'm going to drop the x component here, okay? Now when I do that, something changes. Well, we all know what changes. The velocity changes, okay? So as x changes, the velocity changes if we exert a constant force on it. And I'll remind you that we know the solution to this problem. We could find out how fast it's going. That's what you were doing back in the last unit. Okay? But what I want to say is I want to say that something changes as a result of doing work on it. Okay? In other words, I'm going to say that work is equal to the change in some quantity which I'm going to call k. Okay? That is, the work is equal to the final value of this thing k, whatever it is, minus the initial value of k, whatever this thing is, okay? And that, of course, is equal to f times x. Okay. Now look very carefully at what I'm doing now. The next thing I'm going to do is I'm going to put in Newton's second law. Okay? I told you Newton's second law, Newton's laws is all that there is in all this mechanics stuff. most of the rest of the stuff you'll be doing this semester, it's all Newton's three laws, just some clever new ways to look at them. Okay, so F is ma. X, well, what is x? X is x naught. I said, well, I'm going to call that 0. Okay, the initial velocity, v sub I, okay, times t, plus 1/2 times the acceleration times t squared. Okay, so what I've done is I've taken work and I've written it in terms of Newton's second law and a little bit of kinematics that we know. Well, what we also know about kinematics is that V final is equal to V initial plus AT. In other words, we can write that T is equal to what? VF minus VI divided by A. So I'm going to take that and put it in for T here. Okay, and so now what we have is we have K final minus K initial is equal to MA. Now I got to put all this in. Okay, VI times T, which is VF minus VI divided by A. And then we have plus 1/2 times A times VF minus VI over A quantity squared. Okay? Now the first thing you should notice is that the A's cancel out. Okay? So all the accelerations are now gone. And now I will ask you to do the simple algebra here in order to show that this is equal to 1/2 KF. I'm sorry. Fix that up. It's equal to 1/2 MVF squared minus 1/2 MVI squared. Okay. All right. Let's carry that over to our next page. Okay. So KF minus KI. Okay. In other words, the thing which you change, the amount by which you change this quantity K, is equal to 1/2 MVF squared minus 1/2 MVI squared. So the question is, what is this thing called K? Okay. Is it 1/2 MV squared? I should say, does it have to be 1/2 MV squared? No. We could define K to be equal to 1/2 MV squared plus 17, because then K2 minus K1, I guess K final minus K initial, okay, up here, would still be equal to this, because the 17 from KF would be subtracted out from the 17 from KI. So that's sort of an important thing to learn about energy. Okay, you all know by now, I'm sure, that K is kinetic energy. Okay, kinetic energy is now defined to be 1/2 MV squared. Okay, that's kinetic energy. And what kinetic energy is the energy something has by virtue of its motion. And what you give to a particle when you do work on it is kinetic energy. Okay? In the next video, I'll do a couple of simple examples which show that using kinetic energy and work gives you the same results as you got back in the previous chapter with constant forces. Okay.